Hello and welcome to this pvlib Python tutorial. In this video, we will learn how to use spec sheet data to simulate the module you might have at hand. To do this, I picked a spec sheet from a module from Canadian Solar. I don't have any affiliations whatsoever. I just chose this one because thought it kind of displays what we're dealing with quite nicely. You may choose whatever you want. So we're gonna start by importing pvlib, and from pvlib dot location import location. Then we actually have to import the data from our spec sheet. I prepared a little something here so you don't have to watch me type all this. You will find, most likely, on your spec sheet the standard test conditions, which are the main reference for what we're doing here, and I will choose the values of the first column for this first module here. So I have an operating voltage of 44.1 volt at the maximum power point, and the corresponding current is 9.08. Then we have an open circuit voltage of 53.4 volt and then short circuit current of 9.6 ampere. What does this mean? Actually, over here, we can basically see at the x-axis the voltage, and the point where the graph cuts the x-axis, that's basically the open voltage, the open circuit voltage, which means we have the module and you have like sun shining on it, and you don't have any loads connected to it, so you don't get any current, so the current is zero. And the other extreme, so to say, is the short circuit current on the y-axis, which is another important parameter here, which basically says, okay, we have the PV module under full sunlight, and we just connect positive and negative without any resistance in between, and see what maximum power current can we get from here. And of course, if you do that, the voltage drops to zero. And so these are two references you will find here. What we also have is in the bottom right of this spec sheet are the temperature characteristics. Here you have the temperature coefficient for the maximum power, the temperature coefficient for the open circuit voltage, and the temperature coefficient for the short circuit current. So again, for basically the point down here, the one on the x and y axis, and basically the point where you would get the maximum out of multiplying voltage and ampere, which is your power, and that's the maximum power point where this upper coefficient refers to. So basically says how much does my my value vary with each degree that the module changes from standard test conditions. So those are these three here. As you can see, we have the short circuit current multiplied with the percentage, so the value from the spec sheet divided by 100. Beta VOC is the voltage multiplied with the value, and gamma PDC is just the value itself divided by 100. Okay, now we have the data from our spec sheet. Let's define the module we have, and I'm basically gonna use what I've been using here. So I need my location, that I've been working with. And I will also need the surface tilt and azimuth, which we've been using in the previous tutorials as well. So 45-degree angle and the southern orientation. Then I'm also gonna define the time I want to model my module. So I'm gonna start in 2020 07 01 at midnight. Oops, at midnight, and I'm gonna end in 2020 07 23. Okay. Now I'm gonna use the POA data we've also used before. So I'm just gonna copy the import over here. I don't know if you remember. Oh yeah, we need pandas for this, of course. Import pandas and as SPD. And if you remember, the POA data had quite a weird timestamp. If we have a look at this, it always starts at like 10 minutes past the full hour. So I'm gonna fix this to not run into further issues with this. So I'm gonna say POA data dot index equals pd dot date range. Gonna start in January 2020 midnight. Periods are gonna be the length of the index we already have, POA data dot index, and we're gonna have a hourly frequency. All right, and then I actually just want to have 1 week, the one I defined above. So POA data equals POA data from start to end. And that's what we will use our free frequency, like that. That's the data we want to use with the fixed time stamp. The wind speed is not our index. That was just moved over. All right. Now we have the data. So let's talk about the model we actually want to use, which is the PV watts module of pvlib. This provides us a comparably easy first model that we can use to simulate our custom module. What we have to keep in mind here, we need the POA effective with the angle of incidence losses applied. So we have to consider what happens when the direct sunlight hits the PV module at the orientation that we previously defined. So we have to keep that in mind and calculate this into our POA data. And that's basically what we're going to do now. So we need the solar positions. Solar positions are equal to the location object get solar position. So times actually is the time we defined. Let's get rid of this for now. We defined before, so it's pd dot date range start to end with a frequency again, which is hourly. Good. Then we calculate the angle of incidence, which is calculated using pvlib's irradiance dot angle of incidence. And for this we need our surface tilt, the surface azimuth, the solar position apparent, zenith, the solar position of the azimuth, and did I misspell anything here? Solar, what is wrong? Typo, I'm sorry. All right, now we can calculate the incident angle modifier, which includes the corresponding effects. We use pvlib dot incident angle modifier and the Schrei, and we hand over the angle of incidence that we just calculated, and then we can get the effective irradiance we need by using our PUA data, the PUA direct, and to this we apply the incident angle modifier, and we add PUA data, PUA diffuse. All right, now we have the effective irradiance that we need for the PV watts model. And now the next thing we want to calculate is the effects on the cell temperature that we will observe. So we call this temp cell equals pvlib dot temperature, and we will use the Feynman model where we can easily provide our data. So we will provide the global plane of array, which is in our data, PUA data, PUA global, yeah. Then next we need the air temperature, which is also in our PUA data. Luckily, temp air. The wind speed as well. Wind speed, and that's it. I think, yeah, we should assign this. All right. Now we have a cell temperature, and we can finally calculate the DC output of the module we have at hand. So our resulting DC is pvlib dot pv system dot pv watts DC, and we hand over the effective irradiance we calculated. Then we need to hand over the cell temperature, the PDC 0, which we have up here. So it's the voltage, the power of our module here at the maximum power point, and the gamma PDC equals gamma PDC, which we also defined above, and the reference temperature for the standard test conditions is 25 degrees. So now we can have a first look. Results DC dot plot. I'm gonna enlarge this a little. Big size equals 16 to 9, and result. Let's keep it. PLT dot title is the DC power, and then we say PLT dot plot, but of course show, sorry. To do so, we need to import matplotlib dot py plot as PLT. Yeah. All right, run. Great, no errors, I'm happy. This is our DC output, but of course we want to have the AC output in the end after the inverter. So we're going to use also a simple PV watts model for the inverter. So the results on the AC side are going to be pvlib dot inverter dot pv watts PDC equals result. So the DC time series that we get out of our PV watts DC model, we insert here into our inverter DC, result DC. Then the power of our inverter is defined by PDC 0. Watch out if you want to define this beforehand. For our PV watts model, it's also PDC 0, but this one is a different value. This is the maximum power of the inverter down here. So we can just, well, 500 should be enough. And then we have the efficiency at our invert nominal. I chose values from an pvlib example here, 961, and at inverter for reference is 0.9637. If you have an inverter next to your system, your model, feel free to use those values, of course. So, and then the results AC learner type dot plot big size equals 16.9 PLT dot title AC power PLT dot show. All right, can run this again. Matplotlib has not day of the typos. All right, There we go. So we have our DC output, and of course the AC output is a little lower due to the efficiency of the inverter. And if we would use inverter too small for our output here, it would of course again clip the, let's take 200, make it more impressive. It clips the output of the DC input that we provide here, just like with the other inverter models. All right, that's it for this first basic approach to modeling your own PV module. If you have any questions, comments, or other concerns about what I showed you so far, feel free to leave a comment below. If you like my videos, please leave a thumbs up and subscribe to the channel so other people interested in modeling PV will find my videos on my channel as well. Otherwise, stay curious and we'll meet again for another video. Bye!